Ladies and gentlemen, it's a pleasure for me as President of the Union to introduce to you, however briefly, our speaker, who is Professor Bill Dietrich from the University of California at Berkeley. And he is of course our Arthur Holmes medalist. He received his award yesterday. And today he will treat us to what I'm sure is going to be a marvelous synthesis of his view of his field. And he's also going to speak to young scientists at 5 o'clock today in room 21, at 5 o'clock in room 21. I'll repeat that after his talk. So his talk is entitled The Three Grand Challenges in Geomorphology: Rock, Climate, and Life. Professor Dietrich.
I feel like I'm going to get orthodontry here. Well, first of all, thank you very much. I can now say, my fellow EGU members, thanks to this medal that I've received. It came as a great shock, and I appreciate this very much and the generosity of EGU to give me an opportunity to speak to you as well. I assigned myself what might be considered by some a kind of old-fashioned sounding title: Rock, Climate, Life. And in fact, it is old-fashioned. This is from the Henry Mountains monograph by G.K. Gilbert, in which, in the section on land sculpture, where he's looking at the erosional exposure of the laccolith that he was studying, he mentioned the survival of the hardest, the influence of climate, and the conservative influence of vegetation. Now, we could go today and restate that as, how can we predict mechanistically the erosion rate of bedrock landscapes? How do processes and rates of transport shift with climate? And is there a topographic signature of life? Now, I want to take you through these questions and come back and suggest that those three words, rock, climate, life, are actually really serious challenges and opportunities in the field. And I'm going to look at it through a particular prism, and that prism is the conservation of mass equation. Because after all, if we're going to try to predict the evolution of landscapes, we need to be able to define our terms and solve this equation. And of course, I'm going to point to the right. Sometimes I'll point to the left. I apologize. I can't do this. There's, of course, the surface elevation change term. There's an uplift term. There's erosion of bedrock. And there's a spatial divergence of sediment transport that we have to know. And we'll ask our tectonic friends to give us an uplift field. And we can specify initial and boundary conditions. But what are the expressions that we're going to use that we can call geomorphic transport laws in here? What do we use? I'm going to suggest there is a thing out there that's a geomorphic transport law. It's a hypothesis as much as anything. It's a mathematical statement derived from physical principle or mechanism which expresses the mass flux or erosion caused by one or more processes in a manner that can be parameterized from field measurements. They are identifiable, meaningful parameters in the expression. That it can be tested in physical models. Not all cases, but in some cases we hope to do that. And can be applied over geomorphically significant spatial and temporal scales. So I'm saying it's a hypothesis. These laws are waiting to be discovered. And we need them to put them in the conservation of mass equation to be able to go forward with landscape evolution models in a way that we have some evidence that the expressions we're using are appropriate. So we come back to this, and in essence, we can say this is all of geomorphology in one equation. So how do we do this? Well, we take the expression and we head out to the field, or numerically, we consider a landscape in which we look at the various processes of production of soil, the transport down the channels, and the routing out of the system. And we identify those components and attempt to write expressions for that. This is my favorite cartoon of this. Here's a slice through a hillside, bedding this way, deep-seated landslide on the bedding plane here. I go for a walk up this channel. I take the tributary. I arrive at a landslide scar. I climb up in the hillside, come over to here, and dig a pit. And this is where things begin. Rock becomes soil, and therefore it becomes mobile. Some process causes that material to go down toward the valley axis. It accumulates. Water concentrates, generating a landslide scar. The landslide is mobilized as a debris flow which sweeps down the canyon, not only removing material, but cuts the valley, and then adds sediment to the main channel, which picks up that sediment and cuts the channel by carrying the sediment. So if I wanted to build a geomorphic a landscape evolution model for this landscape, I need a transport law to produce material, to move material to the valley axis, to predict the size and location of timing and landslide, to predict the debris flow incision process, and to predict the fluvial incision process. And each of these have their own length scales, their own physical controls, and we need to break them apart, identify them, quantify them, and build them back into a landscape model. So, but what can we learn at the very beginning of this that says this is a fruitful path? Well, as Smith and Brotherton showed, that if we just hypothesize two things, let's hypothesize that flux is proportional slope. If we start with a flat surface and lower each sides of the surface at a constant rate and evolve a landscape, it will, over time, develop a convex up profile, and it will erode at a constant rate. And that surface then, if we perturb it in some way, the low points will concentrate sediment and it'll smooth out. And so we call this a diffusive process. It'll damp out perturbations. If you take the same approach with this hypothetical landscape, but have water in there and therefore a distance dependency in the flux, you get a predicted concave up profile, and if there's a disturbance to the surface, then the concentration accentuates the erosion and there's incision and perturbations grow. So we can make a landscape if we have a diffusive process and add it to an advective process, and you get ridge and valley topography. So this is an example from Taylor Perrin's modeling, where he's taken the diffusion equation in advective terms and evolved the landscape over time, found a characteristic length scales from the Peclet number of the ratio of diffusion and advection, and predicts a wavelength. And here's showing the increasing effect of advection driving, and therefore increasing narrowing the distance between the channels because the advective intensity is greater. And examining actual landscapes, Taylor was able to use the length scale predicted from the Peclet number to predict the wavelength of these features. So we see as a first order explanation then of landscapes from this transport law perspective is that hill slopes are kind of diffusive and channels are advective. And so if you have a model that has those two elements, you're going to get landscapes that look about right. What do we do here? What does this tell us about this place? This is a crater wall on Mars. And look at the wavelength there. Can we back work toward mechanisms from using these transport laws? And do these transport laws need to be more specific to do that? Well, let's open up the box a bit. And let's go back to that first place where I dug a pit and said I have to make soil. And let me extend that a bit. Here's three layers: fresh bedrock, weathered bedrock, soil. And to solve the erosion transport process here, I have to explore what controls the transition from rock to weathered rock, from weathered rock to soil, the flux by sediment transport down the hillside, and the chemical erosion process through here. If I were to attempt to write the equations, there's an equation for the thickness of the weather zone, there's an equation for the soil thickness, there's an equation for the surface. And we would need to identify a transport law that converts rock to fresh rock to weathered rock. A transport law, if you will, that converts weathered rock to soil. We need a chemical erosion law, and perhaps we need to add dust from above. So just this simple exercise, I left one out, we also, of course, need the flux law for the sediment material, for the granular material. So to just do this problem, we open up a wide array of needs to be able to predict these landscapes. Early on, Arjun Hyvasath took after one of those problems, which is a conversion of rock to soil. And he took cosmogenic radionuclide measurements here and calculated the conversion rate and found an inverse exponential function for that for most of the sites. So as a first approximation, we could call that a transport law. Many things to explore which controls these parameters and exponents, but there's a start. And this has been shown to be useful in a wide range of environments. When you look at the transport, a first approximation seems reasonable to call it a linear dependent transport. In this case, we're looking at transport on a grassy hillside in California. That's a gopher mound, probably causing a transport. That's the state flower, the California poppy, and that's the state shoe. If you take a step back, Josh Rurian and Jim Kirshner hypothesize an expenditure argument for what might actually be a more generalized form of this transport, and obtained data from cosmogenic measurements again to measure flux rate as a function of slope, and also did flume experiments on this and found that a more general expression would be one that's nonlinear, that's linear at low slopes and then turns toward, becomes strongly nonlinear at steep slopes, approaching a threshold slope. So here's a geomorphic transport law for flux down a hillside by this non-water transport process. When we combine the two, we can then have an expression for I'll try to look this way now for a while, that gives us a prediction of soil variation across the landscape. Bright red is thick, blue is thin, and we can use that for a variety of other things. For example, to feed a landslide law, because landslides, when there's cohesion, are dependent upon soil depth. More recently, Effie Fufo and others have got us to think about landscapes even in another way. To point out that if we go to some local place on a hillside, we tend to think of flux-slope relationships as being very local. But the fact is the disturbance up here can carry a long ways down slope. And there's a less of a distance here and a greater distance here that can be influenced by non-local processes. So Effie has proposed that the local gradient may not be fully representative of the active transport process, and that if we look up, we can look farther up slope for where flux can come, and therefore a fractional derivative approach is instructive. And using this approach, she arrives at an expression similar to the Rurian-Kirchner expression. So now we're opening up the possibilities of non-local effects, and this becomes particularly relevant when we think about life. We don't have a landslide transport law. Sorry. Please find one. Please solve this problem, because it acts on a lot of the landscape. There is a sense that we know a lot about overland floor erosion, and we do, on the shorter time scale and on the localized land use effect scale, and now in ecohydrology some. In geomorphology, in the application toward longer timescales, we resort to arguing that flux is proportional to some excess force, or even reduce it to an area as a surrogate for depth or discharge and slope dependency. As far as I can read the literature, while we have mechanistic understanding of event space, we do not yet have a geomorphic transport law for overland floor erosion, but many groups are beginning to construct this by trying to account for vegetation, infiltration, etc. River incision drives landscape evolution. And you can think of there being three processes that do that. There is the debris flow scour that I mentioned at the beginning. There is the picking up of those particles and pounding in the bed of bedrock incision, and there's nick point migration. The first attempt at this, to build a transport law or erosion law, is the simplest you could think of, which is simply argue that erosion rate is proportional to the stream power per unit bed area. That's discharge times slope divided by width, raised to some exponent times some coefficient. Extremely simple. If you say, let's replace discharge with drainage area, it seems like a reasonable idea. Replace width with drainage area, channels get bigger with, or replace width with area because channels get bigger down slope. And then if you also, for simplification purposes here, assume that channel incision uplift rate eventually reach an equilibrium, you can reduce this expression to this form and actually solve for the relationship between slope and area and uplift in a beautiful analytical solution that predicts an inverse power law relationship between slope and drainage area, with these m and n's having to do with the relationships on slope and area, and explicitly uplift in there. So we expect with greater uplift a displacement of the profile. This expression has been used a lot and productively to explore a relationship between uplift and erosion and actually look for faults. It's been a very powerful outcome. But there's more, of course, happening. There's the particles. What do they do? They're not in that expression. Incision rate depends on three things. The amount of erosion per impact, we could write an expression for that. It depends on grain size and velocities. The impacts per area per time, which must depend to some degree on flux. And the fraction of the bed area exposed, which should be some function of flux as well. Leonard Sklar developed the theory and then did experiments in these tubes and found the following outcome, which is as sediment supply increased, there was first an increased erosion, but with increased sediment supply, the coverage went up, and the erosion went down to the point where there was no erosion. So identifying two effects, a tools and a coverage effect, that are great influences on the rate of erosion. So now we see the role of particles in this problem. If you break down the problem in terms of how steep a channel should be for a given area, you can, the slope will be influenced by having to move a certain grain size, there's that slope component, having to carry a certain flux, that's the flux component, slope component of flux, and then having to cut through rock. And I will confess that when we started this, I assumed that the third term was dominant. But it turns out in the theory, and there's some evidence in the field, that in fact the dominant control on slope is grain size and flux, and only secondarily is bedrock resistance important. So when we go back to our slope-area relationships, we have to now look through that and say, what's the signal of sediment? And is the sediment itself a function of uplift in some way? And so the connection is a little different than we imagined. Now, if we look farther upslope, we can see that those landslides mobilize the debris flows, and it is the case that the channel network above about a slope of 10% or so in many landscapes is a result of periodic debris flow incision. So here's that power law relationship we expect from the fluvial processes, but at some transition, in looking at places around the world, commonly at around 10% or so in slope, we see a flattening, a change in the process where evidence is that debris flow predominates. So if we do not want to project the fluvial processes to the divide. There's another process taking place. And there's John. And so one way to do this is to do experiments, to figure out how debris flows cut bedrock. So over here we have a 4-meter diameter vertically rotating drum where Leslie Shih did her PhD work on looking at what controls the collisional force in the boundary and the corresponding erosion rate. And found a relationship between a non-dimensional erosion term and the intensity of impactors, if you will, on the boundary. That one. But also, when you do stuff like this, you see amazing sorting patterns that obviously would have some significant influence on the depositional pattern that happens and also the erosion pattern. And we're collaborating with Kimberly Hill and Barakat Johannes on, this is a discrete element model approach, which reproduces the sorting pattern rather nicely and also actually does a pretty good job of predicting the boundary forces that then we want to relate to the incision process. So in this rush presentation, I've tried to give you a thumbnail sketch, a simple overview, not complete, but to point to this idea of building geomorphic transport laws and how they vary with type of process, they have their own scale dependencies, and those scale dependencies have expression in the landscape, whether it's convex or concave, whether it's the break and slope between the debris flow and the fluvial processes. So when I look at a landscape like this now, I see a channel network where the red areas are swept by debris flows. And the blue areas are clearly in the fluvial domain, and the green area are transitional areas of really interesting sediment transport geomorphic processes, where the river is being handed big rocks that it has to transport in some way. So we come back to this and say, okay, we can use this approach to define a slope as a first approximation, a diffusion advection term. It will give us topography that will that looks and can be found to be similar to what we find in nature. But where is all this stuff about climate, geology, and life? I haven't said anything about that, really. Where does this come in? This is what I want to emphasize now. Can we just stuff geology and life and climate into exponents and coefficients, or do we need a different approach? So I come back to this problem. How can we predict mechanistically the erosion rate of bedrock landscapes? Well, okay, in the river incision process, Leonard found a very nice association between the rate of erosion and the tensile strength. And people are using this result to bring in rock hardness into the erosion law in a nice way. Folks who work on glacier erosions by and large assume that erosion is proportional to the velocity of the basal ice and have had success in reproducing landscape processes and the features that have been created by onset of Pleistocene glaciation. But what do we do here? What do we do here? As far as I know, if you give that as a picture or a topographic map, and I told you the rock type, and I told you the climate, and then said, what's the erosion rate? I don't know anybody who can answer that question. I don't know how to begin the problem. This is the picture that bothers me the most. This is entirely a bedrock landscape. It's obviously breaking down into small pieces and coming out, generating beautiful debris flow levees and flux out. How do we approach this problem? How do we predict erosion of bedrock landscapes? That's a fair amount of the Earth. I don't know. I can't write anything down. It's an area that's, I think, a key area that we need to explore. There are various ways to go, and I don't want to suggest that in any way that what our group is doing is alone in this. There are many groups pursuing this interesting question. But one approach that could be used is to go to a place where a channel is cut between very different rock types. Here's quartzite and schist. And the quartzite is eroding at about 7 meters per million years based on cosmogenics, and the schist is close in geomorphic terms at 5 meters per million years. And yet they have so we see two rock types that have dramatically different basic properties, and one is sticking up and is bare bedrock, and the other is soil mantled. This seems like the kind of natural field experiment we can find where we can start asking the questions, what have been the trade-offs here? What's the mechanical process of breaking down the rock? What has caused this one to be soil mantled and this one not? And how do these two landscapes, so different materials, keep up with each other to a common boundary condition? There's been a lot of recent work on bedrock breaking, and in particular the effect of topography on breaking that Martel most recently has explained in a beautiful way that landscape under compression will, when you create a curved surface, generate tensile stresses on the surface and it will crack the rock. And so the idea is that as ridge and valley topography develops, the tops are intrinsically cracking. And that is breaking the rock down in a way that makes it mobile, but also will profoundly affect the hydrology of the system. And this leads to another point, which is that this ridge then fracturing can also there can also then be a water table beneath the ridges, and the position of the water table itself may affect the degree of breakdown and weathering of the rock, such that below the permanently saturated rock, the rock is essentially unweathered and unfractured, and above there's a fractured zone. So that there's another control on perhaps where that transition from rock to weathered rock is, which is where the permanently saturated ground is. This is suggesting to us, the field, us, that there's an unexplored region beneath the ground surface, this near-surface shallow fractured rock zone that has first-order influence on processes, on the way that water gets off the landscape, on the chemical erosion paths, on the availability of water in the rock to vegetation, a thing we might call rock moisture, and on the slope stability processes associated with exfiltration gradients out of the bedrock and the landslides that might occur, or a weakening along this boundary that causes landsliding. So this is, if you like, a shallow frontier in the field. So if we take a step back then, you could say that if we try to move toward a geomorphic transport law perspective on the effect of bedrock, we need theories that gives us prediction of cracking and the grain size produced by cracking. We need theories that predict the block failure, granular transport, granular wear along paths, and the mass failure and runout caused by debris flows. And there's a start on this. There's a start on this. But I strongly appeal to others to join in on this very difficult but fundamental problem. Okay, how do processes and the rates of transport shift with climate? And is there a topographic signature of climate? Here's a small quiz. You always want a quiz to see if you're even with me or you're not nodding back. There are 4 landscapes. What's the relative erosion rates? Have you made an opinion? This is a Taiwan. This is 5,000 meters per million years. This is the Oregon Coast Range, 100 meters per million years. This is the Atacama Desert, 1 meter per million years. And this is the Brazil area I showed you before of 5 to 7 meters per million years. The curious thing, these 3 landscapes have essentially the same mean annual precipitation. And if we're going to search for some kind of pattern of erosion and climate, it may be difficult to do for a variety of reasons, which I'll explore. Clearly, this dry area does have lower erosion rates. One of the most powerful analysis that's been done in the field is this by Sean Willis to suggest a linkage between incision and tectonics. And this has ignited a huge area of research. The idea in colliding plates that there's uplifted mass, but there's erosion. And if erosion in some way is proportional to precipitation, then the greater erosion on one side of a mountain or the other, here's the topographic surface, here's the precipitation, here's the resulting extremation, will lead to a dramatic change in the configuration of the topography and the mountain and the tectonic processes themselves, so that we see rocks that enter here, arriving here, that is, water draws the rock to it. This precipitation pattern then can affect the height, width, and symmetry of mountains. And so there's been a tremendous effort to explore this idea further. Can we find field evidence of it? One recent example is by Thide et al. In the Himalaya, where they use thermochronology and other measures to try to get at the rate of extremation as it might plot against mean annual rainfall that we can measure contemporarily. They concluded that they could not see a clear precipitation dependency, but they also acknowledged that in the fast rates there, the method they're using may be relatively insensitive. This is an area of, I won't try to wade very deeply in this. This is an area of very active research to try to find the climate signal that's affecting uplift. And there's been some nice studies done that suggest localized effects and cause what's been called tectonic aneurysms, local uplift. But this is still an area of empirical investigation that is being explored, and trying to separate out climate from tectonics on erosion rates is not an easy problem. One dramatic example of this is the drifting of Australia northward. This is reported in Cohn et al., in which you see the calculated denudation rate of Australia using thermochronology, and finding as Australia drifted northward, it descended into the dry zone and the erosion rates dropped off precipitously. So we can see clearly in essentially a tectonically inactive environment that climate then can have a clear signal. Another approach is to go through a climatic gradient, such as along the Atacama, in the Atacama Desert area from the hyper-arid to the semi-arid region. Justine Owen, working with Ron Amundsen, did erosion studies here, looking at the rate of conversion of rock to soil and then removal, and found that going from hyper-arid to semi-arid, to arid to semi-arid, there was a clear increase in the erosion rate. And then beyond that, using other data, there seems to be no dependency. What she concluded was that going from the hyper-arid to the arid zone, that with increasing rainfall, more runoff occurs, which cuts channels more rapidly and drives increased hillslope erosion. The salt-covered hillslopes here give way to absolutely barren rock and then to vegetated landscapes. So the basic idea is that when it's dry enough, the channel incision rate is inhibited. And so the pace of landscape erosion is inhibited. So it's through the effect of what controls how fast the channel cuts down that it feeds back on the pace of landscape erosion. And if it gets dry enough, the channels just can't cut fast enough. I should add, it gets dry enough and on smaller scales, where there just isn't enough water to cut the channels. So if we talk about getting towards a geomorphic transport law for climate, then what it suggests is that we say that channel incision, which we're emphasizing, is driven by discharge and by sediment supply. There is the stream power argument. Here is the sediment supply observation and the theory that go with it. We need to predict the size and amount of sediment delivered to channels, the size of sediment to channels. At this point, I know of no theory to do that. There's been some starts, but we need to be able to take some knowledge of rock and weathering processes and predict the size of material entering a channel and the amount the rate at which it's being delivered. Excuse me. Curiously, we also need to go beyond seeing discharge as being a surrogate for mean annual precipitation or vice versa, and talk about what's the discharge that actually is responsible for cutting channels. And there's been a number of recent studies by some of the people in this room on the really interesting problem of what sets channel scale, channel width, as it's cutting through bedrock. Because curiously, that's a first order effect on the rate of incision. So now we see a coupling between two problems that we don't have good answers for, which is what's the climate discharge relationship that will be important in channel incision, but what sets the scale of a channel? There is, for at least alluvial systems, and maybe there's progress being made in bedrock systems, we don't have a general theory for channel width. And we certainly don't have a theory for how channel width scales or depends on climate. So this opens up another interesting set of research problems. The dependence on hillslope erosion or climate then is of course mediated through vegetation and weathering production. So as we try to focus on climate, we cannot not consider the effect of vegetation as it influences the processes that we're talking about. And so we can think about where does vegetation and biota come into these processes of transport and weathering. And there's a lot of groups exploring this. So let's go to the third question. Is there a topographic signature of life? Or how does life affect geomorphic processes? This is a question you could ask about this Earth. If life had never emerged, how different would it be? Well, the geochemists can quickly give you answers. There's no issue there. It's a very different geochemical world. But would the plates be the same? Would the extent of granitic rocks, some people have speculated, is dependent upon photosynthesis? Would that be different? Would the landscapes have a different frequency distribution of heights, different channels, different processes? This is not a deeply explored question, but it seems fairly fundamental in reflecting what we know about the world. So we can now look at the Earth, as we all do now, through Google Earth. And here's a Google Earth image. And if we fly it with LiDAR, we can do the following. We can take the returns and differentiate the ground returns from the canopy returns and color code that such that the highest canopy is dark green and the shortest canopy is brown, and create not a photograph, but a digital representation of the biota and the land surface. And that's what this is here. And then I can remove that and see for the first time the topography at the scale at which processes and form are linked. And this leads to the question, what is the role of life? Here we have an abiotic system, windblown sand. Here's perturbation due to the presence of some biota. Here we see the plants forming mountains in distortion of surface. So we begin to see what seems to be a biota control process to larger scale disturbance. But then we see dune prevailing over the plant disturbance. So the question we want to ask is are biota a disturbance on a physical, chemical dominated system, or does it have its own signature and processes, own topographic signature? If we look at this problem that I talked about before of the emergence of wavelength, where Taylor Perrin has shown a very distinct measurable wavelength there, this landscape that he's examined developed underneath a soil mantle with abundant life on it. Would the emergent form have been different in some distinctive way in the absence of life? But even more difficult, would it be different in a way, does life lead a distinctive signature, topographic signature? So I'm not going to walk you through the entire chain of argument this. Instead, I will summarize an effort that we made. Clearly, if you go out in the field, you can find things like termite mounds and gopher mounds I showed you earlier where there's a clear biotic signature. Clearly, biota affect processes at all sorts of length scales and are fundamental to understanding erosion rates. But if you examine the Earth and try to find a topographic signature, as we did in this paper, we were not able to identify a unique topographic signature that only exists because of life. And I still welcome, I put this up for this reason, people who could point to what might be a topographic signature of life itself. But despite that, the pervasive presence of biota is profound on surface processes. We can go back to our transport laws and examine, as Kyung-Soo Yu did, the Roaring expression and open up the box and say that this diffusivity has in it a population density and the power expenditure by gophers in digging around the landscape, and make a prediction between soil thickness and local curvature that's improved if he accounts for the population density of gophers across the landscape. Interestingly, he can assign that 1% of gopher power goes into sediment transport. I have no idea what that means and whether they're unionized. But it's a finding. And so, we're starting. It's, in this way, connecting to a coefficient in an existing transport law. Gabay and Mudd have, through numerical modeling and simulation, attempted to, and with success, reproduce the Heimsath observed production as a function of soil thickness by modeling the periodic pulling up of bedrock and making a soil by using discrete event modeling. So we see the start of a bioto-driven transport process that leads to an explanation of a geomorphic transport law. And so we see the coupling of production and flux and the constant role of life. Another path that's being taken is to create topography by these geomorphic transport laws and then do the extensive work in the ecohydrology sense of routing water and growing vegetation on that. And this work by Ivanov is an example of that. So we see people beginning to do the difficult coupling, explicit coupling of vegetation, land surface models for the climate, hydrology, and geomorphic models. We see the beginning emergence of this exploration of this coupling process. So if we talk about the life and moving toward a geomorphic transport laws, including the effects of life, biota affects nearly all geomorphic processes. There are three general approaches that are being used to pursue the GTLs, geomorphic transport laws. There's upscaling in space and time from local mechanistic models. Overland flow, there's a lot of very valuable work being done on routing overland flow, sediment transport, accounting for vegetation, and so on. That then can be, people are exploring how to scale up to the long time scales and spatial scales of geomorphic transport laws. Or the problem of slope stability models. How do we take a localized slope stability model and apply that across the landscape? Another approach is quantifying the biotic controls on coefficients and exponents in these generalized transport expressions. This is one way to try to bring in biota that then can allow you to ask the question, if the population were to shift due to climate change, how would that affect the rate of transport of material across the landscape? And the third approach is to directly model biotic activity and look at the integral sum of the biotic activity on its consequence for flux and transport and erosion. And all three of these approaches are being pursued that should shed some light on the development of geomorphic transport laws. And I will emphasize here that in the recent years, there's been this emergence of ecohydrology and ecogeomorphology, which is looking at this coupling issue in a very exciting way. And I'll add that there's this summary paper by Reinhardt et al. That stressed the importance of the coevolution of landscapes and their ecosystems. So we see this, in this case, the emergence of almost a new field. And as I look at it from the point of view of the geomorphic transport prism and say, we have an opportunity to go from black box coefficients and exponents to something that has explicitly climate biology and hopefully rock in it. Now, I chose this title of, for my talk as a subset of something that I wanted to mention to you all here, because I'm not sure everyone's seen this report. Landscapes on the Edge report, New Horizons for Research on Earth's Surface, is a document that was produced last year, published 2010. It's online and available, and it reports 9 grand challenges and suggests 4 coupled research programs that would provide an opportunity for discovery and new kinds of research in Earth surface processes. I encourage you to look at that. I think it's a stimulating document. And what I've talked about is, in some ways, a particular subset through there, which is how do we get the transport laws that we need to have to drive our landscape evolution models. So let me conclude with this then. To solve the conservation of mass equation and predict landscape morphodynamics, we need geomorphic transport laws. While valuable first steps have been made, some key processes we currently do not have laws supported by field observations to predict the influence on process and form. Bedrock, climate, and biota. These three grand challenges require collaborations among many disciplines, rock mechanics specialists, climate specialists, ecologists, earth source processes, and so on. It's going to require collaborations across disciplines to do this. So please join us. Thank you.
We will take questions. So, thank you very much. That was a marvelous presentation. I'm delighted to see such a large crowd attending. There is possibility of questions, if anybody would like to pose any questions.
I should have talked longer.
So once again, a wonderful talk. You started by stating you start from a conservation of mass paradigm. A good deal of ecology doesn't start from that paradigm. It starts from a population ecology paradigm. You just talk about merging those because, of course, unless you specify all the species and all the life forms, you do have to go through this conversion of different life forms in different conditions. How do you merge those? So it's two different paradigms.
I appreciate that. For full disclosure, I'm married to an ecologist, and we're still discussing this after 30-something years of marriage. I think the approach, I understand what you're saying. The approach is that we take the view that we look at the consequence of biotic activity on the displacement of mass, whether it's dissolution or physical displacement, and ask how can we then characterize biotic activity. So we're not worrying about mass flux and biotic activity so much as we're characterizing its activity, whether it's a chemical activity or a physical mechanism such as burrowing, and translate that into disturbance in terms of a flux. So we can, to some degree, avoid the problem you're talking about. But as I tried to illustrate from Kyung-Soo Yu's example, if flux rate is dependent upon the population density of gophers, then we're into another domain, because then we have to ask what controls the population density of gophers. In the case of where that area is working, it might be dependent upon the abundance of raptors that fly through the Golden Gate recreational area and prey upon them. And so now we go into an ecological food web theory. So I can sort of see breaking it down to the physical consequence in changing the materials, infiltration, root strains, et cetera, causing, energizing the chemical fluxes, or actually physically moving stuff, and then having to ask the ecologists to tell us how the population dynamics works to influence those processes. Does that seem okay? Okay.
Once again, it's a good start.
It's a start. We got to get there. I mean, I hope that I made it clear that although I can't see a topographic signature of life, life affects everything, and it affects. It actually, let me emphasize one thing: is that I think a lot of the climatic response acts through the biotic response first. And so if we're going to get to the erosional process, we have to know how to deal with the biotic response to climate change. Back there.
Another question back here?
Oh, anybody, sorry.
A lot of the work that you showed where the system didn't have any biota in it and you just looked at the evolution of the geomorphic system, it had a sort of relentless pathway that it was following along. When you introduce the interaction of biota into the system, do you still think there'll be a single relentless pathway that things will go along? Or will coevolution take it in unpredictable directions?
Ooh. Okay, I missed a word in there, so I'm struggling. Something pathway, I just can't hear it, I'm sorry.
Relentless.
Relentless.
Relentless. Deterministic.
Relentless?
Yeah.
Thank you. I think landscapes are relentless. Let's see. I think, can I rephrase the question, see if I get it, is that if you consider an abiotic system and a biotic system, will the form and dynamics of the biotic system create, I think you suggested, an indeterminacy. Is that what you're suggesting in the resulting form?
Yeah, because the biotic system has got its own evolutionary pathway that it wants to go along.
Right. I guess, we'll find out when people get farther into how to couple him. I will confess I have a bias here of what nature tells us, which is that despite all the complexities that life does, we get remarkably regular landforms that clearly evolved and were driven by biotic processes. So whether it's tree throw or gophers or termites, in all those different landscapes where there's been evolution of organisms on this, and there's been migration and climate change, we still see impressively regular landforms. And to me, that suggests that the coupling does not lead to, you might call it indeterminacy, but instead leads to some predictability. So
One more
that's
question?
Would you agree that this dominance of physical processes that you just sort of put down as a statement would break down for the submarine morphologies where construction plays a big role? For instance, the buckets of atolls, the barriers that are made by corals and so on.
Coral is a very fine example of a biotic structure, but I see it as exactly that. It's just a built biotic structure, and I bow to it as a real thing. I don't know whether there's anything on other planets that could look like that by chance, but I grant you that coral reefs, because you're actually looking at, it's like looking at a termite mound. Yes, that's a termite mound. I accept that as a real thing. So I agree with you on that.
Well, that was such a good question. We'll have one more. Peter.
Bill, again, also congratulations for that lecture. You asked whether plate tectonics and climate would make a difference if we would have a different planet. And
yes.
I think this is an excellent question. I just wanted to make a comment. We do know that the Nazca plate has changed its velocity by 30% in the last 10 million years alone. And that's something that is very likely linked to a geomorphic change in the Andes.
Aha. Okay. Thank you. And I want to emphasize there might be a few random petrologists in here. I don't know.
Yes, there are. There's one here.
And I've found a few petrologists who have actually argued, and I turn to you and say, are these guys unusual, or is this something to ponder? Which is, they've said, maybe the abundance of granites on this planet, abundance, not occurrence. I realize water plus basalt gets you granite, but the abundance of granite could be due to biotic activity. President, do you have any opinion about that?
No, but I'd love to discuss it with you.
Okay.
So let's leave the room. Okay, I will thank you once more. It was a pleasure. And I'd just like to remind you that Bill Dietrich is very generously, as a new member of this society, as one of us, he'll be immediately participating as one of us, and at 5 o'clock today in room 21, he'll be available to speak to young scientists. Take advantage of it. Thank you very much.